Hello friends, welcome to session number 7 of chemistry. As you all know, we have started with the 7th lesson of your syllabus, that is elements of group 16, 17 and 18. We started studying this lesson and we learn about the general introduction of all these elements, their occurrence, their physical properties, their periodic trends, and their chemical properties. And in the last session, that is session number 6, we learned particularly about the chemical reactivity of all these elements towards certain reagents such as hydrogen, oxygen, halogen, and metals. In this session, we are going to learn about the concept of allotropy and the allotropes of group 16 elements, as well as we are going to learn about the oxoacids of sulfur and halogen along with their structure. So let us start. The first concept we are going to learn about is allotropy. And what is allotropy? You all are familiar with this word. Now, the definition. It is defined as the ability of certain elements to exist in more than one physical form. Do you remember last year we learned about the allotropes of carbon, which are those diamond, graphite, fullerene, etc., where carbon exists in different physical forms. So that is allotropy. Now we will see the allotropy shown by elements of group 16. All the elements of group 16 exhibit allotropy. We will see one by one. First member oxygen, it has two allotropes. One is oxygen itself and second one is ozone. That is O2 and O3 are the allotropes of oxygen. Second member sulfur. Sulfur exists in number of allotropic forms. So many allotropic forms of sulfur are available, but the most important allotropes are rhombic sulfur, that is alpha sulfur, and second one is monoclinic sulfur, that is beta sulfur. Both these forms are non-metallic. Next member is selenium. It also shows two allotropic forms. One is a red colored non-metallic form and second is a gray colored metallic form. Next member is tellurium. Tellurium also exhibits two allotropic forms. First one is crystalline and second one is amorphous. Last member, polonium. It also reveals two allotropic forms. Both are metallic. First one is alpha polonium and second one is beta polonium. So these are the allotropic forms of all the elements of group 16. But we are going to say in detail as per your syllabus about the allotropes of sulfur. So let us start. As you know, as I have told you just now that sulfur exhibits numerous allotropic forms, but the important are only two. The first one is rhombic sulfur, that is alpha sulfur, and second one is monoclinic sulfur, that is beta sulfur. The structure of both these forms is like this. It has 8 atoms in it and which are arranged like this, and the structure is called as puckered ring structure, or it looks like king's crown. So it is also said as king's crown structure. So puckered ring structure or king's crown structure. Okay. Now we are going to compare between these two forms of sulfur, that is rhombic sulfur and monoclinic sulfur, considering different points. So the tabular form of comparison is like this. So we will start with the first point we are going to consider is color. If we consider the color of both the forms, the rhombic sulfur is pale yellow colored while monoclinic sulfur is bright yellow colored solid. Shape of these two allotropes is like this. As the name suggests, the rhombic sulfur or alpha sulfur is orthorhombic in shape, while monoclinic sulfur is a needle shaped crystal. Melting point. Rhombic sulfur has melting point 385.8 Kelvin, while that of beta sulfur with 393 Kelvin. Density, if we consider, beta sulfur has somewhat less density than that of alpha sulfur. So, 2.069 per cubic centimeter is the density of rhombic sulfur, while 1.989 per cubic centimeter is the density of monoclinic sulfur. If we consider the solubility, both these forms are insoluble in water, but both are soluble in carbon disulfide, that is CS2. Stability. Now, about stability, these both forms are interconvertible. They are stable at certain temperature. The temperature which acts as a boundary between these two forms is 369 Kelvin. 369 Kelvin, below this temperature, that is below 369 Kelvin, alpha form is stable. And above 369 Kelvin, beta form is stable. That means uh, alpha sulfur gets converted into beta sulfur above 369 Kelvin. So this is all about stability. Now if you see the structure, we just have seen the structure, puckered ring structure, both of them exhibit same structure. Now method of preparation. If we consider a rhombic sulfur, it is prepared from roll sulfur by evaporation in carbon disulfide. That means, what is roll sulfur? Roll sulfur are sticks of sulfur. So lumps of sulfur we can say. So these roll sulfur, it is evaporated in carbon disulfide and we get alpha sulfur. Beta sulfur is prepared from rhombic sulfur itself. Rhombic sulfur is melted in a dish and it is cooled. Then the upper crust is formed, that is upper layer gets solidified, and below that crust liquid form is present. If we create two holes in that crust and pour out the liquid below it, then that liquid comes out as beta sulfur in the needle shaped crystalline form. So these are the methods of preparation of alpha and beta sulfur. So these are the points of distinguishing points between alpha and beta sulfur. Now, next we will consider oxoacids. What are oxoacids then? The acids containing oxygen, simply we can define. These are called oxoacids. So, we will consider the oxoacids of sulfur. Now, sulfur, again, it forms a number of oxoacids, but out of which some oxoacids are unstable, which are present in aqueous solution in a stable form in the form of their salts and which cannot be isolated. But still, there are various oxoacids which are stable and we will see one by one. So, some important oxoacids of sulfur and their structures are like this. First one, it is sulfurous acid and the formula is H2SO3. Now, you have to see the structures carefully because in exam you might be asked to draw the structures or to explain the structures. Now all these structures have one thing common, that means they contain only three elements: hydrogen, oxygen and sulfur. Again, all these structures contain at least one SOH bond and at least one S double bond O bond. S double bond O and SOH is common in all these structures. So let us start. The structure of H2SO3 is like this. Contains sulfur attached to two OH groups by single bond, one oxygen atom by double bond, and there is one lone pair. So this is the structure of sulfurous acid. Second is sulfuric acid. You are all familiar with this acid, and that is H2SO4. Now, the structure of sulfuric acid is like this. It contains two SOH bonds and two S double bond O. That means it has two hydrogen atoms, one sulfur, and four oxygen atoms arranged like this. So it is stable form of sulfuric acid and most widely used form of sulfur. Now, next acid is di or pyrosulfuric acid. The formula is H2S2O7. Di, that means it is a dimer. That means two sulfuric acid are attached to each other by O single bond O, and one molecule of H2 is removed. Like this. That means they contain two H2SO4 molecules combined by O single bond O. And the structure is like this, hence it is di or pyrosulfuric acid. Next acid is peroxy monosulfuric acid. Peroxy, as the name suggests, it is sulfuric acid containing one oxygen more. And where it is located, the structure is similar to H2SO4, only one oxygen more it is attached here. So it is peroxy monosulfuric acid. Next one is peroxy disulfuric acid. Disulfuric acid. Again, it is a dimer. And the structure is like this. Here you can see the two sulfuric acid molecules are attached by single oxygen atoms. And the structure is like this. One more acid, oxoacid is possible, and that is thiosulfuric acid with the formula H2S2O3. What is difference here? There is S double bond S bond, while all other are same. So these are the oxoacids of sulfur. Now, we will consider the oxoacids of halogens, all the halogens. Halogens, they also form several oxoacids, but only four oxoacids have been isolated in pure form. Which are those? Those are hypofluorous acid, HOF, perchloric acid, that is HClO4, iodic acid, that is HiO3, and the last one is metaperiodic acid or metaperiodic acid, we can say H2IO6. Understood? Now, all these acids are strong acids, but the acidic strength of these acids increases with increasing oxidation state of halogen. In all these oxoacids, halogens exhibit different oxidation states, and as the oxidation state goes on increasing, their acidic strength also goes on increasing. We will consider total all the oxoacids of halogens in the tabular form, and the table is like this. Now, first one we will consider is fluorine. Fluorine can form only one oxoacid, that is hypofluorous acid. The name is hypohalous, that is here it is hypofluorous with oxidation state +1. All other forms are not available with fluorine. With chlorine, all the forms are available. The first is hypochlorous acid with oxidation state +1. Second is chlorous acid, HOClO, or we can say HClO2 with oxidation state +3. Third one is halic acid, that is chloric acid with the formula HClO3, oxidation state +5. The last one is HClO4, that is oxidation state is +7, and the name is perchloric acid. As oxidation state goes on increasing from hypochlorous acid to perchloric acid, their acidic strength also goes on increasing. That means perchloric acid is the strongest acid of all the oxoacids of chlorine. In the same way, bromine also undergoes variety of oxoacids. First one is hypobromous acid with oxidation state +1. Next one is bromic acid with HBrO3, oxidation state +5, and perbromic acid with oxidation state +7 and formula HBrO4. Iodine also forms number of oxoacids. First one is HOI, that is iodous acid with oxidation state +1. This one is iodic acid with the formula HiO3 and oxidation state +5. HiO4 is periodic acid with oxidation state +7. So if we compare all these oxoacids, as the oxidation state goes on increasing, their acidic strength also goes on increasing in this manner. So this is all about the oxoacids of halogens. Now, in your syllabus, structures of oxoacids of chlorine only are included. So we will consider now the structures of oxoacids of chlorine one by one. As you know, first member is hypochlorous acid with the formula HOCl. Now again, all these oxoacids contain one hydrogen, one oxygen, and one chlorine at least. Only three elements are there, and their arrangements. And all these arrangements contain one OH group there attached directly to chlorine. Okay, so let us start. First structure, as you see, OH group attached to chlorine directly. Second oxoacid of chlorine is chlorous acid. Formula HOClO, or we can combine it as HClO2. And the structure is like this: HO directly attached to chlorine, and chlorine now directly attached to oxygen with the double bond. Second one is chloric acid HClO3, that means one oxygen extra. Where will it go? It will directly attach to chlorine with double bond. Now last acid is perchloric acid, again one oxygen extra. Here also that oxygen gets attached with the double bond to chlorine. The structures are almost similar, containing one OH bond and one OCl bond, and the extra oxygen is attached to chlorine directly with the double bond. So these are the structures of oxoacids of chlorine. Now, time for assignment. What will be the assignment today? First is compare or distinguish between rhombic sulfur and monoclinic sulfur, that is alpha sulfur and beta sulfur. That table I have shown you, you will get that in your textbook as well. So draw that table and write the points of differences between alpha sulfur and beta sulfur. Second question is, draw the structures of oxoacids of sulfur. So you have to write the name of that oxoacid, its oxidation state in bracket, then its formula, and below it draw the structure. So you have to draw structures of oxoacids of sulfur as well as structures of oxoacids of chlorine. So these three questions you have to write as assignment. First one is distinguish between alpha sulfur and beta sulfur. Second one is draw the structures of oxoacids of sulfur along with their oxidation state. And third question is draw the structures of oxoacids of chlorine along with their oxidation states. Thank you.